If you're enjoying these astronomy sleep stories, you can support the channel with a quick like and subscribe. And if you feel like it, drop a comment telling me what city or country you're listening from. I actually read those. Now lower your screen brightness, get comfortable, and let your mind slow down. Tonight, we're drifting into the story of Neptune. Neptune is the kind of planet that feels like it was made for quiet curiosity. It doesn't blaze in the sky the way the bright planets do. You can't casually spot it and feel like you've discovered something. Neptune stays far, faint, and patient, as if it's content being a secret at the edge of our neighborhood. And because it sits so far from the sunlight out there is thin and cold, like a distant memory of warmth. If you could stand above Neptune's clouds and look toward the inner solar system, the sun wouldn't feel like a blazing disk. It would look more like a bright star that happens to be your home. That distance changes everything, and it's the first thing to let your mind rest on. Neptune is not just a planet. It's a different environment entirely, a world built from ice and gas and pressure, shaped by forces that don't exist in your daily life, moving to a rhythm that's slow enough to calm you. Neptune is called an ice giant, but that name can be misleading if you imagine a frozen rock with a crust. Ice in planetary science often means something broader: water, methane, ammonia, and other compounds that behave like ices in the cold outer solar system, but under immense pressure can become fluids, slurries, exotic phases of matter that don't show up on Earth outside of labs. Neptune likely has an outer atmosphere made mostly of hydrogen and helium, like a gas giant, but with more ice components mixed in, and beneath that atmosphere, the planet transitions into layers that may be dense, hot, and strange. If you picture Neptune as a clean marble, that's too simple. It's more like a deep ocean of compressed materials, a world where the concept of surface isn't a solid line you can stand on. Instead, you have clouds, then deeper clouds, then deeper layers where gases become supercritical fluids, where pressure turns familiar substances into unfamiliar states, and where temperature rises as you sink. Neptune is not a place with land, it's a place with depth. And depth is a calming idea when you think about it the right way. The deeper you go, the quieter your imagination becomes, because it stops trying to picture details and starts accepting scale. Neptune's atmosphere is famous for its color, that deep, cool blue that feels like midnight water. The blue isn't paint, it's chemistry and light. Methane in Neptune's upper atmosphere absorbs red light, leaving more blue light to scatter back toward our eyes, and that gives Neptune its calm, ocean-like tone. But that color, as soothing as it looks, sits above a planet that is anything but still. Neptune has the fastest winds in the solar system, winds that can reach incredible speeds, screaming around the planet in bands and storms. It's one of the strangest contradictions in the solar system. Neptune receives very little energy from sunlight compared to Earth, yet its atmosphere can be wildly active. You'd expect the farthest planets to be sleepy, slow, frozen in place. Neptune isn't. Neptune moves, it churns, it breathes storms and shears cloud layers past each other like a living machine. That contradiction is one of Neptune's main mysteries, and it's also part of what makes it feel hypnotic. How can a planet so far from the sun be so energetic? One answer is that Neptune seems to generate more heat internally than it receives from the sun, meaning the planet has its own source of energy, leftover heat from formation or slow gravitational contraction, and that internal heat can drive convection, warm material rising, cool material sinking, creating weather patterns and fueling winds. On a world made of fluids, heat is motion, and motion becomes storms. If you listen to this as a sleep story, you don't need to solve the equation. You can just let the image settle. A blue planet in deep, cold space, its sunlight weak, but its interior still warm enough to stir the sky into high-speed flows. Neptune's story isn't just about what it is, it's also about how we found it. Because Neptune wasn't discovered the way most planets were discovered, it wasn't just spotted and named by someone looking up. Neptune was predicted. It was found because another planet was misbehaving. Uranus didn't follow its expected orbit perfectly, and careful observers noticed the mismatch. Something unseen was tugging on it, something with mass hiding in the dark. That realization is one of the most beautiful moments in science. You can't see the thing, but you can see its fingerprints in motion, so you infer its existence from the way it pulls. Mathematicians worked out where a new planet might be, and astronomers pointed telescopes to a patch of sky and found Neptune near where it was predicted to be. It was as if the universe left a clue, and humans learned how to read it. Neptune, in that sense, is a planet discovered by thought before it was discovered by sight. That makes Neptune feel like a quiet reward for patience and precision, a world that was hiding, but not perfectly, because gravity always leaves evidence. Neptune sits about 30 times farther from the Sun than Earth does. A year on Neptune is long, so long that a single orbit around the Sun takes about 165 Earth years. That means Neptune has only completed a little over one orbit since its discovery in the 1800s. Imagine that. We discovered it, and only recently has it circled once and come back to the same position relative to the Sun. Its seasons exist because Neptune is tilted, but they're slow seasons, decades long. A Neptune summer is not a vibe you live through. It's a phase your great-grandchildren might still be in. That kind of timescale can make your own worries feel smaller in a gentle way, not in a dismissive way, but in the way that reminds you there's room to breathe. Neptune is huge compared to Earth, but smaller than Jupiter and Saturn. It's dense enough to suggest a significant amount of heavier materials inside, not just hydrogen and helium. The planet likely has a small rocky core at the center, surrounded by a thick mantle of ice materials, water, ammonia, methane, compressed into hot, dense fluids, and above that, the gaseous outer layers where clouds form. Somewhere in those depths, pressure climbs so high and temperature rises so much that carbon might behave in bizarre ways. There's an idea, still debated in details, that in the deep interior of Neptune and Uranus, methane could break apart under pressure, and carbon could crystallize into diamonds, falling like diamond rain through layers of supercompressed fluid. Whether that exact picture is perfect or not, the deeper point stands. Neptune is a planet where familiar chemistry becomes alien, where the same atoms you know arrange themselves into forms you've never seen. It's a place where rain might not be water, where clouds might be methane or other hydrocarbons, where lightning might flicker through a cold sky for reasons that feel far from home. And floating above it all is one of Neptune's most graceful companions, Triton, its largest moon. Triton is unusual because it orbits Neptune backward compared to Neptune's rotation, suggesting it might have been captured. A visitor pulled in by gravity long ago rather than formed neatly in place. Triton is cold and bright, and it has hints of geological activity, nitrogen geysers or cryovolcanism, a surface that looks like it has been renewed in places. In a sense, Neptune doesn't just have a moon, it has a story of capture, a story of a wandering body becoming bound. That theme, gravity turning wanderers into companions, echoes throughout the outer solar system, and it fits Neptune perfectly, a planet that itself was discovered through gravitational evidence. So when you think of Neptune tonight, you can let it be three things at once: a deep blue world far from the sun, a planet whose weather moves fast even in cold darkness, and a planet whose existence was proven by invisible pull before it was confirmed by a human eye. Let those ideas settle slowly. A distant sun like a bright star, a planet made of layers, more ocean than land, built from pressure and cold. winds racing over blue clouds, a long year taking 165 Earth years to complete, a moon moving backward, captured long ago. Neptune doesn't demand that you hold all the details. It just invites you to drift with it, out beyond the inner worlds, to a place where time stretches and the night sky feels deeper. And next, we'll move closer into Neptune's atmosphere, its storms, its strange dark spots, its cloud bands, and why a planet so distant can still be so alive with motion. Neptune doesn't ease into its personality. The moment you try to picture it clearly, it hits you with its biggest contradiction. A planet that lives in deep cold, far from the sun, and yet has winds that can outrun anything in the solar system. It's like finding a blizzard that somehow knows how to sprint. If you want to fall asleep to Neptune, the best place to start is the atmosphere. Not as a technical diagram, but as a moving, layered world of cloud and pressure, where weather isn't a small daily event, it's the planet's main language. Neptune's sky is mostly hydrogen and helium, the lightest gases, but it's seasoned with methane, and methane changes what you see. Methane absorbs red light, leaving the reflected light more blue, so Neptune wears that deep ocean color that makes it look calm from far away. But calm is just the color. The movement underneath can be intense. Neptune's clouds form at different altitudes, and the planet's atmosphere is arranged in bands, not always as visibly striped as Jupiter, but still structured, zones and belts where winds flow at different speeds and sometimes even in different directions. Those wind patterns can create shear, where one layer slides past another, and shear is a powerful ingredient in storms. Neptune's winds have been measured at speeds that are hard to believe if you're used to Earth, hundreds of miles per hour, and in some cases well over 1,000, depending on how you define and measure the flow. On a planet where the air is thin compared to a solid surface you could stand on, you might imagine wind would feel meaningless. But on Neptune, the atmosphere is the world. Wind isn't moving over the planet. Wind is moving the planet's visible skin. When the atmosphere is your surface, wind is everything. The reason Neptune can sustain so much motion isn't just sunlight, because sunlight out there is weak, like a distant lamp. Neptune's storms and winds likely draw energy, or from internal heat, heat left over from formation and slow release from the deep interior. Neptune radiates more energy than it receives, meaning it's still letting out warmth from within. And that warmth rises through layers, driving convection. Warm material rises, cool material sinks, and in a rotating planet, rising and sinking doesn't just make simple loops. It gets twisted by rotation into jets, bands, and spinning systems. Rotation is the invisible sculptor of weather. Neptune spins in about 16 hours, fast enough to shape its atmosphere into organized motion. Fast enough that storms can hold structure, fast enough to create that steady sense of a planet that is always in motion even though the sunlight is faint. One of the most famous features ever seen on Neptune was the Great Dark Spot, an enormous storm system discovered by Voyager 2 when it flew past Neptune in 1989. If you picture Jupiter's Great Red Spot, you can imagine something similar in concept. A large, long-lived vortex, like a massive hurricane. Neptune's Great Dark Spot was darker than surrounding clouds, a giant oval-shaped storm. It wasn't just a pretty shape. It was a clue that Neptune can organize energy into stable storms, even at the edge of the solar system. And around that dark spot, bright clouds were seen. High-altitude clouds that formed like banners. Possibly methane ice clouds riding above the storm. Those bright clouds looked like streaks and puffs, the way thin clouds on Earth can be pulled into shapes by strong winds, except here the chemistry is different and the scale is huge. But what makes Neptune even more interesting is that its dark spots don't seem to be permanent the way Jupiter's Great Red Spot is. Later observations from powerful telescopes showed that the great dark spot vanished. Other dark spots appeared, drifted, changed, and disappeared. Neptune's storms can be large and intense, but not necessarily immortal. That gives Neptune a different kind of personality. It's not a planet with one famous storm that lasts for centuries. It's a planet where the atmosphere is dynamic enough to create giant vortices and then dissolve them back into the flow, like the planet is constantly remixing itself. That's a calming idea if you let it be. Nothing holds forever, not even storms on a world of wind. Neptune's bright clouds are also part of its charm. Sometimes you see bright patches near the poles, sometimes bands, sometimes small streaks. These can be methane ice clouds, forming when air rises and cools, allowing methane to condense into crystals. On Earth, rising air cools, and water vapor condenses into clouds. On Neptune, rising air can do the same general thing, just with different chemicals and different pressure levels. The cloud tops you see are like a thin layer of visible texture on a much deeper system. Beneath the bright methane clouds might be deeper clouds of other compounds, and deeper still, the atmosphere becomes dense and hot enough that the idea of a cloud becomes more abstract, more like gradients of composition and phase than fluffy shapes. And yet, even with all this complexity, Neptune's weather can feel simple in the way oceans feel simple. A surface in constant motion, patterns that repeat, waves of circulation, storms that come and go, all driven by energy moving through a fluid. If you imagine watching Neptune from far away, you might see slow changes. A bright cloud drifting, a dark spot evolving, a band shifting. But if you could speed up time, Neptune would look alive, like a globe of blue smoke constantly reshaping itself. That's the kind of mental image that helps you relax. A world moving, but not toward any goal, just moving because that's what fluids do under heat and rotation. Another detail that makes Neptune feel like a real place is the way its poles behave. The polar regions can show different cloud activity and sometimes bright features in the outer, and planets' poles can host unique circulation patterns, vortices, polar clouds, sometimes even persistent systems that are different from the mid-latitudes. On Neptune, observations have suggested complex polar activity, and in recent years, scientists have tracked changes in Neptune's clouds and brightness that hint at seasonal behavior. Neptune's seasons are extremely long, decades, and because Neptune's orbit takes about 165 years, the planet's climate shifts are slow enough to be subtle, but not so slow that they never show up. The way sunlight falls on Neptune changes over time, and that can influence where clouds form, how bright the atmosphere appears, and how heat is distributed. It's not a fast season like a human season, it's a generational season. Neptune's sky changes the way a coastline changes, slowly, with patterns you only notice if you pay attention for long enough. And that is exactly how Neptune is studied. Not through one snapshot, but through patient watching across years. Neptune also has faint rings. They aren't bright like Saturn's, but they exist, thin arcs and ring segments made of dust and small particles. Some of Neptune's rings are incomplete looking, concentrated into arcs rather than uniform circles, and those arcs are thought to be maintained by gravitational interactions with small moons, little shepherds that keep ring material corralled into patterns. Rings aren't just decoration. They're physics made visible. They show gravity shaping debris into structure. They show that even in the emptiness around Neptune, there are delicate systems balancing motion and stability. And when you think about those rings while thinking about Neptune's winds, you get this layered image, storms and clouds racing around the planet, and above them, faint ring arcs quietly circling like dust caught in a slow dance. Neptune is not just a blue ball, it's a system. It has weather, it has rings, it has moons, it has a magnetic field that behaves oddly, and it has internal heat that keeps its atmosphere active. It's a world built from layers of motion on top of layers of pressure, with delicate structures like rings floating above and captured companions like Triton moving below. If you want to sink into the mood of it, imagine being far out there where the sun is small. Imagine watching Neptune's clouds through a telescope that sees blue and white and faint shadowed spots. Imagine knowing that what looks calm from far away is actually moving at incredible speeds, like a silent storm you can't hear. Imagine the planet's year stretching across human lifetimes, seasons sliding from one to the next, so slowly they feel like a background hum rather than a change. And let your mind rest on the simplest version of the mystery: a cold planet with fast winds, a distant world that still has energy to spare. Next, we'll go deeper, not just into the weather you can see, but into Neptune's hidden machinery, its interior layers, its unusual magnetic field, and what it means to be an ice giant where the surface is only the beginning. Neptune looks like a calm blue sphere from far away, but the deeper truth is that Neptune is not a planet you can draw with clean layers and call it finished. It's a world where the word surface doesn't really apply, because everything you'd normally stand on is replaced by depth. More atmosphere, more pressure, more heat, more strange states of matter the farther you go. And that's part of what makes Neptune feel so soothing to imagine at night. It's a planet that invites you to stop thinking in sharp boundaries and start thinking in gradients. On Neptune, things don't suddenly become something else. They slowly become denser, warmer, heavier, darker, until the only way to describe the planet is by how it changes as you sink. The outermost layer is the atmosphere, mostly hydrogen and helium, with methane mixed in, and that methane is the reason Neptune looks blue. But the atmosphere isn't just air, it's a moving, layered fluid. At the top you have high clouds, where temperatures are low enough for methane to condense into crystals and form bright patches. Beneath those clouds, pressure increases steadily. Imagine it like diving into an ocean, except the water is gas becoming thicker until it behaves more like liquid. The deeper you go, the less the word gas feels correct. Eventually you reach a region where the gases are so compressed that they behave as supercritical fluids, states of matter that are neither gas nor liquid in the normal sense, but something in between, dense and penetrating, a phase that doesn't have a clean surface. It's like the atmosphere turns into a deep, heavy ocean of compressed material. Below that outer layer, Neptune likely transitions into what's often called the mantle, though it's not a mantle like Earth's rock mantle. In an ice giant, the mantle is thought to be rich in what planetary scientists call ices: water, ammonia, methane, and related compounds. But ice here doesn't mean frozen cubes. Under Neptune's pressures and temperatures, these materials become hot, dense fluids, water that isn't liquid like a lake, but something far more compressed, ammonia in a state that doesn't resemble household chemistry, methane behaving in ways that make it less like a gas and more like a component in a thick, high-pressure mixture. This mantle is where the planet's weirdness becomes truly unfamiliar. Temperatures climb, pressure climbs, chemistry changes, molecules break apart and recombine. You get ionic and metallic phases, forms of matter that sound like science fiction, but are simply what happens when you squeeze substances hard enough and heat them enough. One of the most famous ideas about Neptune's deep interior is diamond rain. The basic thought is that methane molecules, under extreme pressure, can break down, freeing carbon, and that carbon could crystallize into diamonds. Those diamonds, being dense, would sink, falling through the mantle like glittering hail in a dark ocean. Whether the process happens exactly like the popular image is debated, but the concept captures something real. The interior environment is so extreme that it can turn familiar compounds into unexpected materials. Neptune is the kind of planet where carbon can become a storm, where rain might mean solid crystals sinking through fluid layers, where the word ocean doesn't guarantee water in any Earth-like sense, just a thick body of compressed substance. And deeper still, there may be a rocky core, a dense central region made of heavier elements, silicates and metals, small compared to the planet's overall size, but massively influential in terms of gravity and structure. Neptune is not mostly rock. It's mostly the stuff between air and rock, between gas and liquid, between chemistry, and chemistry you can only imagine. That interior isn't just a curiosity. It drives the planet's behavior. Neptune radiates more heat than it receives, meaning it has internal energy leaking outward, and that internal heat helps power the fast winds and storms you see. The interior heat is like a slow furnace that never fully turned off. A leftover glow from formation and gradual contraction may be combined with phase changes inside, releasing energy as the planet slowly settles. On Neptune, weather isn't just sunlight stirring air. Weather is deep heat rising through layers. That's why Neptune can be so active despite being far from the Sun. But one of Neptune's most fascinating hidden features isn't something you can see with your eyes at all. It's its magnetic field. If you picture Earth's magnetic field, you might imagine a bar magnet, north and south aligned roughly with the planet's rotation axis, centered fairly neatly. Neptune's magnetic field doesn't behave like that. It's tilted significantly relative to Neptune's rotation axis, and it's offset from the planet's center. That means Neptune's magnetosphere, the region where its magnetic field dominates, can be weirdly lopsided and dynamic as the planet rotates. Imagine a magnetic field that wobbles around like a lantern swung in a slow circle, sweeping space with an asymmetrical pattern. The effect is that charged particles around Neptune experience changing magnetic conditions, and the interactions with solar wind and with the planet's moons can be complex. This odd magnetic geometry also hints at something deeper. The magnetic field is likely generated not by a molten iron core like Earth's, but by electrical currents in the planet's interior layers, possibly in an electrically conducting fluid region within the mantle, where water and ammonia under pressure become ionic or conductive enough to support a dynamo. In other words, Neptune's magnetism may come from a middle layer rather than the very center. That's a beautiful thought if you let it be. A planet whose heart isn't the only thing that shapes it, a planet where the magnetic engine might live off-center in a deep ocean of strange conductive fluid. Neptune's magnetic field shapes its auroras. Light shows near the poles where charged particles interact with the atmosphere. Auroras on Neptune are harder to observe than Earth's because of distance, but the concept is the same. Invisible particles guided by invisible fields colliding with atmospheric molecules and releasing light. It's one of the quietest and most elegant ideas in planetary science. A planet can glow at its edges because space itself is not empty, because fields and particles are always moving, always interacting. Neptune's magnetosphere can also trap particles, forming radiation belts. These belts and fields can interact with the planet's rings and moons, shaping how dust moves and how charged grains behave. Even the rings, faint as they are, exist inside a magnetic environment that influences tiny particles. Everything around Neptune is part of a connected system. Deep interior heat influences atmospheric motion. Atmospheric motion influences what we see. Magnetic geometry influences particle behavior. Particle behavior influences rings and space environment. It's all tied together by gravity and rotation and time. Rotation is another quiet ingredient you can feel without seeing. Neptune spins in about 16 hours, so the planet has a day-night rhythm much faster than its year. But the day-night contrast is not like Earth's because sunlight is weak and the atmosphere is deep. Still, rotation shapes everything. It organizes wind into jets. It shapes storms into spinning systems. It influences how heat moves outward. It also influences the planet's shape. Neptune is slightly flattened at the poles, bulging at the equator due to its spin, like a slow, soft response to centrifugal force. Even its gravity field reveals internal structure, because the way mass is distributed inside affects the planet's gravitational pull in subtle, measurable ways. In a sense, Neptune's interior is something we see by inference, through gravity, through magnetism, through heat, through the behavior of the atmosphere. That's why Neptune feels like a planet built out of hints. We've only had one spacecraft fly by, Voyager 2, which gave us an extraordinary snapshot, but a snapshot is not a lifetime. Neptune's interior dynamics are still being understood. Its storms are still being watched. Its magnetic behavior is still being modeled. Neptune remains partly unknown, and that's part of the mood. It's a planet that doesn't feel over-explained. It feels like a deep place, so if you want to drift with it tonight, picture Neptune as layers. Blue clouds racing at the top, deeper clouds beneath, a thickening atmosphere turning into a dense, fluid ocean, a mantle of hot ices under pressure, chemistry transforming, carbon crystallizing and sinking. An off-center magnetic engine, generating a tilted field that sweeps space unevenly. A small rocky core sitting quietly at the center, dense and heavy, while everything above it moves. And above that whole layered world, faint ring arcs circle like dust caught in a soft orbit. Neptune is a planet you can't stand on, but you can fall into it in your imagination, sinking through layers that get quieter and darker until you stop trying to picture details and just feel the idea of depth. Next, we'll step back out of Neptune's interior and follow the companions that orbit it. Triton's strange backward path, Neptune's smaller moons, and the delicate ring arcs that hold their shape through gravity's quiet guidance. Neptune was predicted before it was truly seen, but it wasn't truly known until one brief visitor crossed its neighborhood and sent back proof in the form of images, measurements, and quiet surprises. Voyager 2 is the reason Neptune stopped being just a mathematical conclusion and became a place with texture. And what makes that moment feel almost unreal is how fast it happened compared to Neptune's own time. Neptune takes about 165 Earth years to circle the Sun once. Voyager 2 flew past Neptune in 1989 and had only a short window to look, like someone walking through a massive cathedral with just enough time to glance up at the ceiling before the doors close again. That's the mood of Voyager at Neptune, a fleeting encounter with a distant world that moves slowly, captured in a hurry, then left behind. Voyager approached Neptune after already visiting Jupiter, Saturn, and Uranus, and by the time it reached the outer edge, it was already a seasoned traveler, an instrument of curiosity moving through a quiet, cold region where sunlight is thin and radio signals take hours to cross back to Earth. When Voyager 2 arrived, Neptune wasn't waiting politely. It was active. It showed bands. It showed bright clouds. It showed a large, dark storm system, what became known as the Great Dark Spot, like a bruise in the blue. The storm was massive, roughly Earth-sized in scale, and it immediately changed how people thought about Neptune's atmosphere. Before Voyager, Neptune was a distant blue dot with hints of brightness changes. After Voyager, Neptune was a world of weather, a planet that could build large vortices and whip winds around itself at astonishing speeds. Voyager measured wind speeds that were almost insulting to intuition. A planet far from the sun, a planet with weak sunlight, producing winds that can rip across cloud tops faster than anything on Earth. That single fact has kept Neptune mysterious ever since, because it implies a powerful internal engine. Neptune isn't just reflecting sunlight, it's moving heat from within, turning internal warmth into atmospheric motion. Voyager also revealed Neptune's bright methane clouds, sometimes appearing as streaks and patches, often near storms or in higher latitudes, thin and luminous against the deep blue background. Those clouds weren't just decoration. They were evidence of vertical motion, air rising and cooling and condensing methane, the outermost visible layer of a much deeper system. And around the great dark spot, Voyager saw bright companion clouds, like a storm wearing a crown, suggesting intense atmospheric dynamics, shaping cloud formation at high altitudes. But here's the part that feels quietly perfect for a sleep story. Neptune's great dark spot did not become an eternal icon the way Jupiter's great red spot has. It vanished. Later observations showed Neptune's big dark spots can appear and fade, migrating and dissolving over time. That means Neptune is a planet that doesn't cling to the same face for centuries. It remixes, it reshapes, it makes storms, and then lets them go. If you want to fall asleep to Neptune, that's a comforting pattern. Even the biggest turbulence eventually smooths out. Voyager also brought attention to Neptune's rings. Neptune's rings are faint, and before Voyager, evidence suggested Neptune might have rings, but their true structure wasn't clear. Voyager confirmed them and showed something stranger: arcs, incomplete ring segments concentrated in certain regions. At first glance, it seems like those arcs shouldn't exist. Ring particles should smear into a uniform ring over time. But Neptune's arcs persist because of gravitational relationships with nearby moons, resonances that keep particles corralled like dust trapped in a repeating rhythm. Voyager's images made those arcs real. They turned a theoretical ring system into a delicate, visible pattern. Thin lines of debris and dust held in place by nothing but gravity and time. It's one of those details that makes the solar system feel like it has hidden craftsmanship, not designed, but inevitably shaped into art by physics. Then Voyager turned its gaze to Triton, and Triton stole the show in a different way. Triton is bright, icy, and strangely young-looking in places, and Voyager revealed a surface that didn't match the expectation of a frozen dead world. It showed patterns like ridges and smooth plains and terrain that looked like it had been resurfaced. And the most unforgettable discovery: geysers, dark plumes rising from Triton's surface, likely nitrogen gas erupting, carrying darker material that fell back down and created streaks across the ice. The idea of geysers that far from the sun feels like a secret being let out. Not fire geysers, not water geysers, cold geysers, nitrogen-driven activity under a weak sun. This suggested Triton has energy, and energy means processes, and processes mean that even in the cold outer solar system, worlds can be dynamic. Triton's retrograde orbit already hinted it was captured, likely from the Kuiper belt, and if Triton was captured, the tidal forces involved could have heated it internally, giving it the ability to remain active. So Voyager's flyby didn't just show Neptune's weather, it showed the system's history. A captured moon, faint rings shaped by moons, a planet with strong internal heat, and a magnetic field that doesn't behave politely. Neptune's magnetic field, measured by Voyager, is tilted relative to its rotation axis and offset from the planet's center, creating a magnetosphere that is lopsided and complex, not the neat, symmetric field you might imagine. That odd geometry hints that Neptune's dynamo, the mechanism generating its magnetic field, might operate in a different layer than Earth's, likely within an electrically conducting fluid region in the interior rather than a molten metal core. It's another Neptune theme. The important engine may not be at the center. It may be in the deep middle, where pressure turns ice materials into conducting fluids, where chemistry becomes electric. Voyager also measured Neptune's temperature structure and atmospheric composition, deepening the understanding that Neptune is an ice giant, not just a smaller Jupiter, and that its interior and atmosphere are enriched differently, giving it its own identity. But for all Voyager revealed, it also left a quiet frustration that you can feel in the way people talk about Neptune. We've only been there once. One flyby, one moment, one set of images. And Neptune is not a planet that can be finished in one visit. Its storms change, its seasons are long, its brightness varies, its magnetic environment shifts. You can't fully understand Neptune with a single glance because Neptune doesn't hold still for you, and it doesn't move on human timescales in the way we'd prefer. It's the same reason Neptune feels so soothing as a sleep subject. It doesn't care if you're impatient. Neptune will still be Neptune long after your curiosity has drifted off, still rotating, still blowing winds, still cycling slow seasons, still holding its secrets in deep layers. And there's something calming about a world that isn't solved. It lets your mind relax, because you don't have to complete it tonight. You can just sit with what we know. Voyager showed Neptune as a blue planet with violent winds, large storms, bright methane clouds, faint rings with arcs, and a captured moon that erupts. And what we don't know sits quietly beneath that. How exactly Neptune generates and maintains such high wind speeds, how its interior layers are structured in detail, how its storms form and dissipate, how its long seasons shift cloud patterns over decades, how Triton's interior works, what Neptune's rings look like up close, how the magnetosphere interacts with the solar wind in real time. Neptune remains unfinished, which is exactly the kind of thought that lets you exhale. You can imagine Voyager 2 as a tiny moving dot of metal, crossing Neptune's vastness at high speed, cameras clicking, instruments listening to fields and particles, then continuing outward into darkness, leaving Neptune behind like a dream you woke from too soon. And Neptune keeps spinning without noticing, a planet so far away that its sunlight is faint, but its own inner warmth still stirs its atmosphere into motion, its blue color holding steady while the details shift and change. So as your eyes feel heavier, let this be the main image. Neptune, discovered first by math, then briefly visited by Voyager, revealed as a world of fast winds and changing storms, with delicate rings and a strange captured moon, and still, despite that reveal, remaining one of the most quietly unknown planets we have. Next, we'll drift into Neptune's long time, its seasons that last decades, the slow, changes observers have tracked from far away since Voyager, and what it means to study a world that refuses to hurry. Neptune doesn't live on human time. That's one of the best things about it if you're trying to relax, because it pulls your mind out of the short, noisy rhythm of your day and into a slower rhythm where change happens like drifting clouds rather than sharp headlines. Neptune spins fast, about 16 hours for one rotation, but its year is enormous. It takes roughly 165 Earth years to go once around the Sun. That means a season on Neptune isn't something you experience. It's something you inherit. It's something you measure with patience. And because Neptune's sunlight is weak and far away, the seasonal changes are subtle, not like Earth's obvious shifts of warm and cold, green and brown. Neptune's seasons are more like gentle rearrangements of cloud patterns and temperature gradients, quiet changes that you only notice if you watch for years and keep your records. That's the kind of science Neptune demands. Not urgency, but attention. Neptune has an axial tilt, like Earth, meaning it has seasons because different hemispheres receive different sunlight over time. But because its orbit is so long, each season lasts for decades. Imagine a summer that lasts longer than most human lifetimes. Imagine a winter that settles in and stays, not as a sudden cold snap, but as a slow adjustment in how sunlight touches the planet's atmosphere. You might think seasons wouldn't matter much on a world so far away, but they do, because even small changes in sunlight can influence how heat is distributed in an atmosphere and on a planet where internal heat is important too. The interplay between internal warmth and external sunlight can shape circulation patterns in complex ways. Neptune isn't only warmed from above, it's also warmed from within. That internal heat is steady compared to the seasonal sunlight changes, but sunlight still matters in the upper layers where clouds form and where the visible atmosphere responds. So Neptune's seasons may be less about temperature swings and more about where the atmosphere decides to put its clouds. One of the ways scientists study Neptune's slow change is by watching its brightness and cloud activity over time. After Voyager 2's flyby, Neptune didn't stop evolving. Astronomers using powerful telescopes, space-based and ground-based, have tracked bright cloud features, dark spots, and changes in the planet's overall appearance. One of the most striking things is that Neptune's large, dark storms seem to come and go. Voyager saw the Great Dark Spot. Later, it vanished. Other dark spots have been observed since, forming at different latitudes, drifting, changing shape, and fading. That tells you Neptune's atmosphere is dynamic, and not in a steady, predictable way. It's dynamic in the way a fluid is dynamic. Patterns emerge, hold for a while, then dissolve. Neptune isn't carving one permanent symbol into its atmosphere. It's continuously remixing. That matters because it suggests Neptune's weather is driven by deep processes, convection and heat flow, and also shaped by upper atmosphere conditions and seasonal sunlight. It's like a planet-scale soup that never settles. The bright clouds on Neptune are often methane ice clouds at high altitudes. These bright features can appear suddenly and move quickly, riding winds that can cross huge distances. Sometimes these clouds seem to cluster near certain latitudes, and sometimes they pop up like flashes. To watch Neptune's bright clouds is to watch the atmosphere reveal itself briefly, then hide again. It's similar to watching thin clouds on Earth at sunset. You see the motion, you see the texture, and then the pattern changes and it's gone. Because Neptune is so far away, the details are harder to see, so each observation feels like a glimpse of something that keeps moving when you look away. That creates an almost dreamlike relationship between humans and Neptune. We observe, we infer, we model, but the planet remains partly out of reach. Neptune also has a strange relationship with temperature. You'd expect the upper atmosphere to be cold, and it is, but measurements have shown that Neptune's stratosphere and upper layers can show unexpected temperature behavior, and some changes over time have been observed. On a planet this far, temperature isn't just how much sunlight hits it. It's also about how heat is transported upward, how gases absorb and emit radiation, how methane and other molecules affect thermal structure, and how seasonal sunlight changes the chemistry and circulation of the upper atmosphere. Even the color and brightness can be influenced by haze formation and methane distribution. Neptune's deep blue isn't just a paint job, it's a living result of chemistry and light. If methane concentration changes with altitude or location, or if haze layers thicken or thin, the planet's appearance can shift. It might be subtle, but it's real. That's what makes Neptune feel alive, even though it's not alive. It changes, not rapidly, not loudly, but slowly, like a distant ocean under a faint sun. Time behaves differently on Neptune, not just because seasons are long, but because the entire environment is set up for slow processes to matter. In a cold region, chemistry can slow down. Reactions happen at different rates. Condensation and sublimation patterns can shift gradually. Radiation from the sun is weaker, but still present, and cosmic influences can matter. And because Neptune's magnetosphere is tilted and offset, the way charged particles interact with the atmosphere might vary in complex patterns, possibly influencing auroral behavior and upper atmosphere chemistry. It's another layer of slow change, not always visible, but always happening. Studying Neptune from Earth is also a lesson in patience. because Neptune doesn't give you many easy opportunities. It's far, it's faint, it's small, in the sky. It requires big instruments, long exposures, careful processing. And the signals arrive to us filtered through Earth's own atmosphere unless you use space telescopes. So every Neptune observation is like listening to a quiet song through a wall and trying to reconstruct the melody. That's why Neptune still feels unfinished. We've never had an orbiter around Neptune. We've never watched it for years from close range the way we've watched Mars or Saturn. We've had one flyby and then decades of distant watching. That's not nothing, but it's not the full story. Neptune is still a planet we mostly know from hints, patterns, and models, and the difference between one flyby and a long, close study is enormous. A flyby gives you a photograph. An orbiter gives you a movie. Neptune deserves a movie. If you imagine a future mission, an orbiter that could watch Neptune's storms form and fade, track winds across seasons, map temperature changes, study the magnetosphere in motion, watch Triton's geysers and measure their timing, you realize how much is still unknown. You realize Neptune is not a solved planet. It's a waiting planet. And that waiting quality is restful. It means you don't have to force closure. You can let Neptune be what it is, distant, blue, energetic, and slow in its cycles. Neptune's long seasons also make you think differently about the concept of climate. On Earth, climate change can happen on human timescales because our atmosphere and oceans respond quickly in some ways, and because human activity is powerful. On Neptune, the changes are natural and slow, tied to orbit, tilt, internal heat, and chemistry. It's like a laboratory for seeing how a giant fluid world evolves without biology, without continents, without oceans in the Earth sense. Just physics, chemistry, and time. And there's something calming about that simplicity. Not simple as in easy, but simple as in honest. Neptune doesn't have distractions. It's a planet that exists as motion and layers. So let your mind settle into Neptune time. Imagine decades-long seasons sliding across the planet, sunlight shifting slowly from one hemisphere to the other, clouds brightening in some regions and fading in others, dark spots forming and dissolving, winds racing constantly even as the long year continues. Imagine observers on Earth watching with telescopes, tracking tiny changes in a faraway blue disk, building a story out of repeated glances. Imagine Neptune continuing its orbit, quiet, patient, unstoppable, so that long after tonight, long after you wake up, it will still be out there, still moving through its slow season, still stirring its atmosphere with internal warmth, still holding its mysteries in layers, still waiting for the next visitor. Next, we'll tie Neptune's story back to the bigger outer solar system, how Neptune shapes the Kuiper belt, how its gravity influences distant objects, and why Neptune, more than most planets, acts like a gatekeeper at the edge of our planetary neighborhood. Neptune doesn't just sit at the edge of the solar system like a quiet blue decoration. It acts like a gatekeeper. Its gravity reaches farther than its calm color suggests, and over billions of years it has shaped the architecture of the outer solar system the way a slow current shapes a coastline. If you want the most Neptune idea to fall asleep to, it's this. Neptune influences worlds you can't even see, and it does it silently, just by existing with enough mass. The outer solar system is full of small, icy bodies, objects made of rock and ice, leftovers from formation, scattered across regions like the Kuiper belt beyond Neptune, and the more distant reservoirs farther out. Many of those bodies are too faint to notice casually, but they are part of a real population, and Neptune is one of the main reasons that population looks the way it does. Neptune's gravity doesn't only hold moons and rings nearby, it also shapes the orbits of distant objects through resonances, patterns where orbital periods lock into simple ratios, like 2.3 or 1.2, creating stable pathways or unstable traps. Resonances are one of the most elegant ideas in astronomy because they are invisible but precise. They're like grooves carved into space by repeated gravitational nudges. If an object orbits in a resonance with Neptune, it gets tugged at the same point in its orbit again and again, and that repeating tug can either stabilize the orbit or pump it into a new shape. Over time, these resonances can gather objects into families. They can also clear regions out, pushing objects away. When you look at the Kuiper belt, you see structure, not randomness. And Neptune is a major sculptor of that structure. Pluto is the most famous example, and it's worth mentioning because it's a perfect illustration of how Neptune's influence extends beyond what most people imagine. Pluto's orbit crosses Neptune's orbital distance, which sounds like a recipe for collision. But Pluto is in a stable resonance with Neptune. For every 3 orbits Neptune makes around the Sun, Pluto makes 2. That resonance keeps them from crashing into each other because their positions are synchronized in a way that prevents close encounters. Pluto is like a dancer moving across Neptune's stage without ever colliding, because the rhythm keeps them separated. And Pluto is not alone. There are many Plutinos, Kuiper belt objects in the same 2.3 resonance, quietly following similar patterns. That tells you something. Neptune's gravity doesn't just perturb once, it organizes. Neptune also seems tied to the concept of migration, the idea that the giant planets may not have formed exactly where they are now, but shifted over time as they interacted with a disk of smaller bodies. In many models, Neptune may have formed closer to the Sun and then moved outward, or otherwise changed its position as gravitational interactions swapped energy and angular momentum. When a giant planet migrates, it doesn't just move itself, it drags resonances through space like sweeping nets, capturing objects, scattering others, rearranging entire populations. This is one of the most important reasons Neptune is considered a shaper of the Kuiper belt. If Neptune migrated outward, its resonances would have moved outward too, capturing some objects into stable patterns and flinging others into stretched, tilted, eccentric orbits. That's how you can end up with a Kuiper belt that contains both relatively calm, orderly orbits and more chaotic, excited ones. Neptune's long, quiet pull becomes a kind of history-writing tool. Another way to understand Neptune's role is to picture the solar system not as a static arrangement, but as a system that settled. Early on, there were more objects, more collisions, more scattering. Neptune's gravity helped decide what stayed in stable belts and what got ejected outward or inward. It likely contributed to the delivery and removal of icy bodies, potentially sending comets inward toward the inner solar system at times. Neptune can act as a gravitational slingshot. When a small icy body passes close enough, Neptune can change its trajectory, speeding it up, slowing it down, throwing it into a new orbit. Over millions of years, those small interactions add up. Neptune becomes a sorter, a bouncer at the edge of the club, quietly deciding who gets to stay and who gets tossed into the dark. There's a calmness to that image. Neptune doesn't chase anything. It doesn't need to. It just waits, and gravity does the rest. Neptune's link to the Kuiper belt is also emotionally satisfying because it connects back to Triton. If Triton truly came from the Kuiper belt and was captured, then Neptune didn't just shape Kuiper belt objects from afar, it reached out and took one. Triton becomes a physical piece of the Kuiper belt living inside Neptune's system, a captured relic that carries the outer solar system's DNA. That means when you look at Triton, you're likely looking at the kind of object that exists in large numbers beyond Neptune, icy, volatile, rich bodies that may have complex geology and unusual chemistry. Triton is a reminder that the Kuiper belt isn't just a graveyard of frozen rocks. It's a population of worlds, and Neptune is the nearest major planet that sits close enough to influence them strongly. Neptune's influence might even extend to the idea of scattered disk objects, bodies with elongated orbits that take them far beyond Neptune, likely thrown into those orbits by gravitational encounters. Some of these objects swing inward near Neptune, then travel far outward, like comets in slow motion. They exist in the boundary region between the Kuiper belt and the more distant reservoirs. Neptune, again, is a gatekeeper because it can move objects from one region to another. The outer solar system isn't neatly separated by fences. It's a continuum of orbits, and Neptune is one of the main forces that stirs that continuum. And then there's the very far edge, the idea that even beyond Neptune's strongest influence, there are objects in distant orbits that we're still cataloguing and trying to understand, and that their patterns might hint at other influences we haven't confirmed. Neptune's role here is indirect but important. To understand what lies beyond, you need to understand what Neptune would have already shaped. Neptune becomes a baseline for structure. It's the known sculptor you account for before you look for anything else. In a way, Neptune teaches the same lesson as its discovery did. You learn about unseen things by seeing their gravitational effects. Neptune itself was found because Uranus was being tugged, and now Neptune helps us interpret the tugging and structure of distant populations. Neptune is like a chapter in the solar system's detective story. First, Neptune was the invisible cause. Then Neptune became the visible cause shaping other invisible populations. That's a neat loop, and it fits Neptune's whole vibe. Quiet influence, deep effects, evidence written into motion. If you want to picture it simply as you drift off, imagine Neptune as a blue lantern at the edge of the planetary neighborhood, its gravity reaching outward like a slow tide. Beyond it, countless icy bodies orbit in cold darkness, and some of them are in resonant rhythms with Neptune, dancing to a pattern set by a planet they might never approach closely. Some are scattered, wandering in long, stretched ovals shaped by past encounters. Some are captured like Triton, pulled into Neptune's family and made to orbit backward as a permanent reminder that the solar system has a history of grabs and exchanges. Neptune's influence is not loud, but it's everywhere in that region. The outer solar system's structure is not accidental. It's the product of gravity repeated over time, and Neptune is one of the main repeaters. So as your mind slows, let Neptune become what it really is. Not just a distant planet, but a quiet architect. A world that doesn't need to shine bright to matter. A planet that shapes the orbits of distant objects, organizes families through resonances, scatters others into far paths, and stands at the edge like a calm, blue boundary between the inner planet's warmth and the outer darkness. Next, we'll drift into one more layer of Neptune's story that's both practical and strangely calming. What it would be like to visit, what a future mission would actually aim to learn, and why Neptune remains one of the most tempting, unfinished planets for exploration. Neptune is one of those planets that feels like it's always halfway out of reach, not because it's impossible to get to, but because it refuses to be simple. We've only ever visited it once, and the more you think about that, the stranger it feels. A world this large, this dynamic, this influential, sitting at the edge of our planetary neighborhood, and we've only given it a quick glance. If Mars is familiar enough to feel like a destination people talk about living on, Neptune is different. Neptune is not a place you go the way you go to a rocky planet. It's a place you enter with instruments, with probes, with careful planning, and even then, it's not a landing. It's a descent. Because there isn't a solid surface waiting. There's only atmosphere becoming deeper and heavier until it becomes an environment your mind doesn't naturally know how to picture. And that makes Neptune feel like one of the most tempting unfinished worlds, the kind where one more mission wouldn't just add details, it would rewrite the way we understand the outer solar system. The biggest practical barrier to Neptune isn't drama, it's distance. Neptune is far. It takes years and years for a spacecraft to reach it, and the farther you are, the weaker sunlight becomes, which affects power systems. Solar panels that work near Earth become far less effective out near Neptune because the sun is so faint. That means missions to Neptune usually need a different power source, something that doesn't depend on sunlight, so they can operate for long periods in deep space and then do real science once they arrive. Communication is another quiet challenge. Signals take hours to travel. You don't drive a probe at Neptune like you drive a drone. You send instructions, you wait, you receive data later, and you build your understanding from careful, delayed conversation across billions of kilometers. That delay is part of the mood of Neptune. Everything is slow in human terms, but the planet itself can be wild. If we sent a mission to Neptune that could stay, an orbiter instead of a flyby, the first thing it would give us is time. Time to watch storms form, drift, and fade. Time to track wind speeds across seasons instead of guessing from a snapshot. Time to map temperature changes and see how internal heat moves through the atmosphere. Time to observe the planet's faint rings up close, to see how dust particles behave, how arcs are maintained, how moons shepherd and shape the ring material. Time to watch Triton not as one image, but as a living world, tracking geysers, measuring surface changes, mapping composition, understanding whether the moon has a subsurface ocean or internal layers that keep it active. A long mission would turn Neptune from a photograph into a movie, and that difference matters more than people realize. With one flyby, Neptune can feel like a puzzle you briefly saw. With an orbiter, Neptune becomes an environment. You start noticing patterns. You start noticing cycles. You start seeing cause and effect. And Neptune is a planet where cause and effect hide in layers. One of the biggest science questions an orbiter could help answer is the mystery of Neptune's energy. Why are its winds so fast? How exactly does its internal heat leak outward? How do convection and rotation combine to form jet streams and storms at different depths? How deep do the visible storms extend? On Earth, hurricanes are shallow compared to the planet, driven by heat and moisture near the surface. On Neptune, storms could be connected to deeper layers, possibly reaching down into regions where the atmosphere becomes dense and fluid-like. An orbiter with the right instruments could measure gravitational variations and atmospheric waves, helping infer how mass is moving inside and how deep features go. Another major target is Neptune's magnetic field. Because it's tilted and offset, the magnetosphere is complex. Single flyby gives a slice of that complexity, but it can't show the full behavior over time. An orbiter could map the field in detail, measure how it changes, and observe how it interacts with the solar wind and with charged particles trapped around Neptune. It could clarify how the dynamo works, where inside Neptune the conducting fluid region is, how the planet generates such a lopsided field, and why ice giants in general have these weird magnetic geometries. That matters beyond Neptune, because Uranus has a similarly strange magnetic field. Understanding Neptune helps explain ice giants as a category, and that category matters because many exoplanets discovered around other stars appear to be Neptune-sized. In other words, Neptune isn't just about Neptune, it's about understanding a common class of planets in the galaxy. If we don't understand our own nearby ice giants, our understanding of exoplanets is missing a big piece. The rings are another quietly rich science. Target. Neptune's rings are faint and arc-shaped in places. Seeing them up close would help us learn about ring particle sizes, composition, and dynamics. It would tell us how arcs stay confined, how moons maintain them, and whether the rings are young and replenished or old and slowly decaying. Rings are natural laboratories for gravity, collisions, and dust physics. They're like a small-scale version of disk dynamics, the same kind of dynamics that once shaped the disks where planets formed. Watching rings is like watching an old echo of planetary formation still happening in miniature. Then there's Triton, which might honestly deserve its own mission by itself. Triton is a captured Kuiper Belt object, and Kuiper Belt objects are some of the most primitive relics of the solar system's early days. But Triton is not just primitive, it's active. It has geysers. It has resurfacing. It has a strange seasonal cycle because its orbit and Neptune's tilt create lighting, conditions that shift over long times. Triton could potentially have a subsurface ocean, and if it does, that raises the kind of questions that always pull attention. Internal oceans, chemistry, energy, habitability. Not because we're desperate to find aliens, but because internal oceans seem to be one of the more common, hidden habitats in the solar system, places where liquid water might persist without sunlight, powered by tides or internal heat. Triton's retrograde orbit and capture history complicate its internal story, making it a fascinating case. Did capture and tidal heating create conditions for long-lived internal liquid layers? Is Triton's activity fading or sustained? How does nitrogen behave on such a cold surface? What does its geology look like in high resolution? An orbiter at Neptune could watch Triton repeatedly and build a real timeline of activity. Some mission concepts include not only an orbiter, but also an atmospheric probe, a small craft that would plunge into Neptune's atmosphere and send back data as it descends, like the Galileo probe did at Jupiter. That kind of probe could measure the composition of Neptune's atmosphere directly. The ratio of elements, the abundance of methane and other compounds, the distribution of heavier gases, the temperature and pressure profile as you go down, cloud layer depths, and winds as a function of altitude. This is important because remote sensing can infer a lot, but direct sampling settles debates. Knowing Neptune's atmospheric composition helps us understand how Neptune formed, where in the solar nebula it assembled, what materials it accreted, how much ice versus gas it captured, and how the planet's history compares to Uranus's. Neptune and Uranus are similar in size, but they differ in internal heat output. Neptune seems to radiate more heat than Uranus. Why? Did Uranus suffer a giant impact that changed its internal layering and trapped heat? Did they form differently? Did their interiors mix differently? These questions aren't just trivia. They're about how planets become the worlds they are. Neptune, in that sense, is a clue to our own origin story. But even without the technical goals, visiting Neptune carries a quieter value. It expands the mental map of what a world can be. Humans are used to land. We're used to surfaces, mountains, rivers, skies with oxygen. Neptune is the opposite, a world where the ground is pressure, where clouds are chemistry, where wind is the main visible motion, where the sun is small, where seasons last decades, where moons can erupt nitrogen into space, where rings exist as faint arcs held together by resonance. Neptune is an education in humility. It reminds you that Earth's version of reality is one narrow case. The universe builds worlds that don't fit our instincts, and if you let that thought settle at night, it can be strangely calming, because it pulls you out of your daily loop and drops you into a bigger one. So imagine, gently, a future spacecraft approaching Neptune. The planet grows from a dot to a disk, then to a globe. The blue deepens. The bright clouds become distinct. Dark storms appear like quiet shadows moving across the atmosphere. Triton becomes a world, not a point, a bright, icy moon with subtle features. The rings appear as thin threads, arcs that look too delicate to exist. Instruments begin to listen to the magnetic field, mapping invisible shapes around the planet. A probe, if one is sent, falls into the atmosphere, sending back data until pressure and heat overwhelm it. A brief voice from inside a giant world. An orbiter circles, watching storms for months, then years, building the movie we've never had. It doesn't have to be loud, it doesn't have to be dramatic, it just has to watch, That's how Neptune reveals itself, through patient observation. And that's the final mood to rest on for this part. Neptune isn't a planet that you finish by learning one fact. Neptune is a planet you slowly come to know, layer by layer, cycle by cycle, as if the planet is teaching you how to slow down. Neptune's story, when you hold all of it together, feels less like a single narrative and more like a quiet web. One thread is discovery by math. One thread is weather that shouldn't be so fast. One thread is a deep interior that turns familiar substances into alien states. One thread is Triton, the captured wanderer moving backward. One thread is faint rings held in arcs by gravity's repeating nudge. One thread is the Kuiper belt, shaped by Neptune's pull like a coastline shaped by tide. And the final thread is the one that makes Neptune feel so calm to think about at night. Neptune is unfinished, not because it's broken, but because it's so far and so slow that our understanding still sits at the surface layer of what it truly is. If you want a last part tonight that rounds Neptune out without forcing it into a neat bow, the best way is to treat Neptune like a boundary planet, not the end of the solar system, but the edge where the rules begin to change. Inside Neptune's orbit, the solar system feels more familiar. Rocky planets, warmer sunlight, clear surfaces, atmospheres you can model with weather concepts that feel like home. Past Neptune, you enter a region of deep cold and ancient leftovers. Icy bodies, long orbits, faint sunlight, objects that are less like planets in the traditional sense and more like preserved relics. Neptune sits right at that transition. It's the last giant planet, the last major gate before you drift into the belt of remnants. That position makes Neptune feel like a guardian. It marks the end of the main planetary neighborhood and the start of a quieter, older zone. Neptune also shows you that distance doesn't equal deadness. It's easy to assume the outer solar system is sleepy, frozen in place, barely moving. Neptune proves the opposite. Neptune's winds can be extreme. Its storms can be massive, its clouds can shift, its magnetic field can tilt and swing, its moon can erupt, its rings can hold structure. The outer solar system isn't calm because nothing happens, it's calm because the drama is silent and slow in the ways humans don't naturally notice. Neptune's storms don't roar into your ears. They spin in cold blue silence. Neptune's seasons don't announce themselves. They drift across decades. Neptune's influence on the Kuiper belt doesn't look like a shove. It looks like a gentle rearrangement repeated over millions of years. That's why Neptune is such a good planet to think about while you're winding down. It's motion without noise, scale without urgency, change without panic. Neptune also teaches a strange lesson about what power looks like. Jupiter is powerful in an obvious way, massive, bright, dominant. Neptune's power is quieter. It shapes orbits through resonance. It captures a moon and remakes its system. It holds faint arcs of ring material in place through invisible rhythms. It acts as a gravitational filter for objects, trying to move inward or outward. Neptune's power is the kind that doesn't need to show off. It's just there, and over time it becomes undeniable. That matches the way Neptune was found in the first place, not by bright, obvious presence, but by the subtle tug it left on Uranus. Neptune is a planet that announces itself through influence rather than appearance, and even visually, Neptune is deceptive. The deep blue looks calm, like an ocean planet, and it's easy to project peace onto that color. But under that color are winds racing faster than intuition wants to accept. And under those winds is a deep interior, where pressure turns ice into hot, conducting fluids, where carbon might crystallize, where heat leaks outward and feeds the storm layers. Neptune is calm only in the way a deep ocean is calm. The surface might look smooth from far away, but inside, the currents are strong. and the depth is endless. Triton is the emotional anchor if you need one, a moon, captured from the cold outer belt, orbiting backward like it refuses to fully join the family, yet bound by gravity anyway. Triton's geysers are the quiet proof that even in the far cold, worlds can still move and change, and Triton's future, slowly spiraling inward, reminds you that orbits are not permanent. Systems evolve. Even the most stable-looking arrangements can shift over time, slowly enough that no one notices until the change is already written into the numbers. Neptune's rings echo that same theme. They're faint, fragile, and yet they persist. They're held in arcs as if someone cut a ring into pieces and froze it mid-motion. But the reason is simple. Resonance, shepherding, repeating gravitational nudges. In a universe where nothing is trying to be beautiful, physics still creates beauty by inevitability. Neptune's rings are that kind of inevitability made visible. And then there's the larger neighborhood Neptune governs, the Kuiper belt and the scattered objects beyond. Neptune is tied to those bodies the way a lighthouse is tied to a coastline. It sets rhythms, it shapes paths, it marks the boundary between the main planets and the leftover worlds. It's the last major planet before the solar system turns into a wide field of smaller things. That boundary feeling is what makes Neptune so satisfying as a final subject. It's the edge of the familiar. It's the last big anchor before the dark opens up. If you're listening to this and your eyes are getting heavy, you can let Neptune become the last image your mind holds. A deep blue planet in far cold space, a small sun off in the distance, bright clouds sliding across the atmosphere, winds racing silently, a faint ring arc circling like dust caught in orbit, Triton gliding backward with a bright, icy face, and beyond all of it, the Kuiper belt spread out like a quiet field of frozen worlds. Neptune keeps moving through its long year. It keeps stirring its atmosphere with internal warmth. It keeps shaping distant orbits with gravity. It doesn't need attention to keep existing. It doesn't need to be solved tonight. It just is. And that's a good place to leave your mind, with a world that is steady in its motion, slow in its cycles, and quiet in its power, letting you drift the same way Neptune drifts around the sun, unhurried, patient, and calm. Neptune is the planet that teaches you how to think slower. It sits so far from the sun that daylight becomes a distant glow, yet it refuses to be quiet on the inside. A deep blue world made of layers instead of land, where the surface is moving cloud tops, and the real planet is depth, pressure building, heat rising, chemistry turning unfamiliar, matter shifting into forms Earth barely knows. Neptune's color looks calm, but its atmosphere can race with the fastest winds we've measured. Storms can appear like dark bruises in the blue, and then vanish later, as if the planet never wanted a permanent signature. It was discovered the most Neptune way possible, not by being obvious, but by influence, by a subtle gravitational tug that betrayed it before any eye confirmed it. That same influence continues today in the outer solar system, shaping distant icy bodies into resonant rhythms, scattering others into long, wandering orbits, acting like a quiet gatekeeper at the edge of the main planetary neighborhood. Around Neptune, faint rings trace thin arcs of dust held together by gravity's repeating nudges, delicate structure maintained without any solid walls, just orbit and time. And beyond the rings moves Triton, the captured wanderer, bright, icy, orbiting backward like a permanent clue that the outer solar system is full of encounters and thefts, a moon that still shows signs of activity in a place that should be frozen silent. Neptune is unfinished because we've only truly visited once, and one flyby can't capture a planet of decades-long seasons and shifting storms, of tilted magnetism and deep internal engines. But that unfinished feeling is the point. Neptune is a reminder that not everything needs to be solved right now. That distance doesn't equal emptiness, that quiet power can shape whole regions without making noise, and that the universe has worlds that don't fit our instincts but still follow their own steady rules. So if you're winding down, let Neptune be the last image you hold. A small sun far away, a blue planet turning in silence, clouds sliding, winds racing without sound, rings faint and fragile, Triton drifting backward, and beyond it all a cold field of distant worlds moving to Neptune's rhythm, everything unhurried, everything continuing, while your thoughts slow down enough to finally let go.